Good day, everyone. Today, I would like to present to you a topic on energy harvesting performance of a novel polymer nanocrystalline composite of VDF-TrFE with zinc oxide quantum dots films. This research has been performed by several postgraduate students at Low Dimensional Materials Center, University of Malaysia. Before I start my talk, I would like to thank you, the organizing committee of International Research Award on Sensing Technology, for giving us the opportunity to present this work. So in this case, we are going to look at devices that can harvest energy from ambient environment. So to start with, we have to choose suitable materials with enhanced properties, low in cost, and reduced in size. So there are several ways that we can harvest energy from ambient, such as by using pyroelectric effect, piezoelectric effect, and triboelectric effect. We can also harvest energy from thermoelectric by making use of seebeck effect. When there is different temperature at two locations of materials, then we can harvest energy from that effect. So in that case, the material need to have low specific heat capacity, low thermal conductivity, low dielectric loss, and high pyroelectric current. Most of the thing that we consider here in our work, we look at the environmental issues with the materials that we use for harvesting energy. So we are trying to reduce the toxicity in environmental. So in the environment, so we select material which is non-toxic, or in other words, lead-free materials. Young ETL has reported that thermoelectric energy can be harvested from zinc oxide nanowires arrays. So from these zinc oxide nanowire arrays, he has obtained pyroelectric current as much as 1.2 to 1.5 nanocoulomb centimeter square Kelvin, with voltage coefficients of 2.5 to 4 times 10 to the 4 voltage per meter Kelvin respectively. So with that reported research, we are encouraged to look into zinc oxide nanoparticles further. So we knew that zinc oxide nanoparticles has prominent features such as wide direct band gap, a large exciton binding energy of 60 MeV, and it is also non-toxic, which is one of the properties that we are looking for. Furthermore, zinc oxide nanoparticles also has pyroelectric features. So the structures of zinc oxide is wurtzite, so it is under the category of non-central symmetrical structures. It has polar surfaces of zinc oxide, whereby the zinc oxide, as shown in this figure here, the structures of wurtzite zinc oxide as shown in this figure here, has attracted opposite charge ions on its surfaces. So with that, there will be a normal dipole moment along the C-axis of the zinc oxide structure. In this figure, we illustrate the zinc oxide quantum dot that has been synthesized in our work. So it has inorganic core, inorganic shell, and aqueous organic coating with conjugated biomolecules. The polymer host that we have chosen is VDF-TrFE. So in VDF-TrFE, there is hydrogen atoms on one side of the polymer axis and fluorine atoms on the other side of polymer axis, which is in the trans arrangement. So with this kind of structures, PVDF-TrFE has high and stable polarization with short switching time. These properties would be favorable to use as a polymer matrix to form a layer film of polymer nanocomposite. So by introducing a zero-dimensional nanofiller into this ferroelectric polymer host areas, so it would be a great interest to actually look at the particle size effect on their structural and physical properties of the nanocomposite. So the advantage of this ferroelectric composite are they would be light and also flexible, and it will have high pyroelectric and piezoelectric properties. So we can use this type of nanocomposite as sensors, actuators, ferroelectric random access memories, and energy harvesting. So we have two objectives to achieve in this work. One is to improve the ferroelectric and pyroelectric properties of polymer PVDF-TrFE with the inclusion of zinc oxide quantum dots. So we are hoping by including the nanocrystal zinc oxide as fillers into the copolymer, it will increase the polarization and consequently increase the current generated from the pyroelectric activities. Then we are going to assess, will assess the energy storage performance of this PVDF-TrFE zinc oxide quantum dots nanocomposite and look into its potential as energy harvesting device. The PVDF-TrFE thin films are prepared following this flowchart here. So initially we dissolve PVDF-TrFE with methyl ethyl ketone solvent, spin coat at 5000 RPM in 30 seconds, and then annihilate at temperature between 80 to 140 degrees for 1 hour. This picture here shows the sample that has been produced as thin films. So here is the top electrode and the bottom electrode is here, and the yellow color represent the thin films. So then what we do next is we characterize the physical properties of the thin film by using XRD, FTIR, DSC, and also FISAM. The electrical characterization were performed by using ferroelectric tester, dielectric impedance analyzer, pyroelectric quasi-static pyroelectric system, and thermally stimulated current system. Zinc oxide quantum dot is synthesized by following this flowchart. We initially use two solutions, solution A and solution B. The solution A will be reflux and then add with TEA ligand and then reflux again before cool it down to 25 degrees. And after that, the solution B will be added with solution A, precipitate the solution for 50 minutes, centrifuge it at 5000 RPM in 3 minutes, and finally we will obtain zinc oxide quantum dot with TEA in a solid form. So physically, this quantum dot is characterized by using UV spectroscopy, PL, XRD, FISAM, and TEM. So we also look into the electrical properties of this zinc oxide quantum dot by using ferroelectric tester and dielectric impedance analyzer. To prepare a nanocomposite of PVDF-TrFE with quantum dot, zinc oxide quantum dot, initially we prepare the PVDF solution by dissolving it inside methyl ethyl ketone, and after that we add zinc oxide quantum dot solid inside PVDF-TrFE solution. We vary the weight percentage of the zinc oxide quantum dot from 0.15 weight percent to 0.5 weight percent. And this solution will be stirred in ultrasonic bath and also stirred again before it is spin coated at 5000 RPM for 30 seconds. and afterwards it will be annealed for 1 hour at 100 degrees Celsius. So this picture here shows the color that has been produced by zinc oxide quantum dot that we have synthesized from various weight percentage concentration of zinc oxide inside the VDF-TrFE polymer holes. So you can see from clear to blue color emission. We have used several methods to confirm the particle size of zinc oxide quantum dots. So the first method is known as a mathematical model of effective mass approximation. So this is the equations that determine the radius of the quantum dot. So in this equation, we need to know the absorption peak of the quantum dot. So we have to do the UV spectrum. We have to use UVB spectroscopy to obtain the absorption spectrum. So from there, we can determine the peak of the absorption, which is around 280. And then by using this equation here, we can determine the radius and hence the diameter of the quantum dots. So by using that analysis, the particle size is 2.36 nanometer. So from the absorption spectrum, we can also determine the energy band gap of the quantum dot. So in this case, we found that the energy band gap is around 3.7 eV by using tau method, as shown in this formula here. PL is also performed for this work. So we see that blue emission is obtained and centered around 480 nanometer when the zinc oxide quantum dot is excited at 330 nanometer wavelength. Particle size analysis of zinc oxide is also performed by using XRD and also TEM. So from XRD, it indicates that the structure of the zinc oxide quantum dots that we synthesize is hexagonal wurtzite. By using Debye-Scherrer equation, we calculate the particle size, which is about 2.1 nanometer, which is not far off from what we have obtained by using mathematical model. From TEM images and also the distribution of the particles size, we determine that the quasi-spherical shape of this zinc oxide is around 3 plus minus 0.5 nanometer. So from the result that we obtain through UVVs, XRD, and TEM, we can confirm that the quantum dot size that we produce is around 2 to 3.5 nanometer. The purity of the nanocomposite were investigated by using EDAX. So we have obtained EDAX spectrums, and the spectrum reveals that there are strong signals coming from zinc, oxygen, carbon, and fluorine atoms. There's no impurity peaks indicated by the EDAX spectrum. So the presence of zinc, oxygen, carbon, and fluorine atoms was also approved with elemental mapping images. The energy storage performance of this nanocomposite were investigated by using hysteresis loop of ferroelectric properties. So this figure here shows the hysteresis loop of several nanocomposites with 0 weight percentage of zinc oxide to 0.5 weight percentage of zinc oxide inside the polymer host. We knew that polarization can be related to dielectric displacement through this equation as shown here, D equals to P plus epsilon naught E. So in ferroelectric test, we increase the electric field until we reach saturation and then revert the direction of electric field until we achieve the negative saturation state. So once the field is removed, most dipole will not revert back to their original orientation because of the pinning effect coming from microscopic defects within the crystalline lattice. So from this hysteresis loop, we can obtain remnant polarization, which occurs at zero electric field, and also energy storage density, which is shown by the orange color here, which can be obtained from the area of this part of the hysteresis loop, and energy loss density, which is indicated by the blue color of this hysteresis loop. So from this figure, we identify that the loop produced by hysteresis measurement is rectangle in shape, and 0.15 weight% of zinc oxide in the polymer host give the highest remnant polarization, which is as indicated in this figure here. The discharge energy density and also charging energy density with respect to the zinc oxide weight percentage is shown in this figure here. So it is actually calculated from the integrated area according to the polarization hysteresis loop, as we discussed in the previous slide. By using this formula, then we can calculate the energy storage. So from this figure, we note that the highest energy density for this polymer nanocomposite achieved when the zinc oxide composition is around 0.15%. So the energy storage density is around 1.18 joule per centimeter cube, which is close to the what has been reported by other workers by using the polymer of VDF-TrFE CFE at 280 MV per meter. The largest discharge energy density reported is around 21.4 joule per centimeter cube. In order for us to understand why 0.15 weight percentage of zinc oxide inside the polymer host gave the highest energy density, we have performed leakage current measurement. So the result is shown in this figure here. So what we see is the leakage current increase with the increase of electric field, as shown in the figure. The current densities coming from all the composition is ranged from 10 to the minus 12 to 10 to the minus 10, with increasing field up to 140 volt, 40 MV per meter. So the composite increased up to 10 to the minus 11 to 10 to the minus 7 ampere per centimeter square, as zinc oxide quantum dot is increased up to 0.25 weight%, as shown in this figure here. So when we increase zinc oxide quantum dots composition to higher than 0.25 weight%, we can see that the leakage current has increased tremendously, which deteriorate the ferroelectric properties due to the excessive high leakage current density. Energy harvesting performance of this polymer nanocomposite is analyzed by obtaining the figure of merit as shown in this equation here. So figure of merit is obtained from the pyroelectric coefficient, P squared divided by epsilon naught, epsilon r. In this figure, it indicates that when we increase the composition of zinc oxide quantum dots to 0.15 weight%, the pyroelectric coefficient and figure of merit increase tremendously, which is about improvement of 50% compared with the pure VDF-TrFE from 31 to 41 microcoulomb per meter squared Kelvin. However, as the composition is increased above 0.15 weight%, the figure of merit and pyroelectric coefficient is reduced tremendously. So according to Tan et al., the addition of zinc oxide nanoparticle in the nanocomposite thin films enhanced the local electric field during Pauling in a polymer matrix at the boundary of zinc oxide nanoparticle. So the highest or maximum figure of merit obtained from this nanocomposite at 1 kHz is 19.5 joule per meter cube Kelvin square. Morphology structure of PVDF-TrFE zinc oxide quantum dot is also investigated by using VSAM. So the figure here indicates the structure of zinc oxide quantum dots. This is before annealing and this is after annealing at 2 magnification. So from this picture, the annual temperature used is 100 degrees Celsius. So from this picture, we can conclude that the nanocomposite does not affected so much by the annealing temperature of 100 degrees Celsius because in this experiment, the zinc oxide quantum dot is passivated by TEA, which prevent the growth of quantum dots, zinc oxide quantum dots. So the point distribution or morphology from this picture does not differ significantly between the cast and any zinc oxide quantum dots. Morphology structure of the zinc oxide quantum dots in polymer host PVDF-TrFE is shown in this diagram, in this VSAM figure here. So this is for 0.15% weight%, and at the bottom here is for the highest percentage of zinc oxide, which is 0.50. And 1, 2, 3 refers to 3 magnification order of the VSAM. So from this figure, there are 2 types of crystalline exist. 2 types of crystalline exist in the nanocomposite. One is known as spherically shaped crystalline micelle, which is indicated by this sphere here, and also the elongated rod-like structure, which can be clearly seen in this figure here. So as we increase the composition of zinc oxide, what happened is the spherically shaped crystalline micelle has turned into holes. Okay, so you can see clearly in this figure here. So there is a coalescence between crystalline micelle-like structure with the elongated rod-like structure, and it will get saturated at certain weight percentage of zinc oxide. This table in this slide shows the growth of the spherical micelle-like structure and also the elongated rod-like structure. So the length of elongated rod-like structure increase when from 0 weight% up to 0.15%, and then reduce as the weight percentage of zinc oxide increase. So the diameter of spherical micelle increase at 0.15, reduce and increase again after the zinc oxide weight percentage is increased. So the distribution of this saturated agglomeration increase with increasing zinc oxide quantum dot, exceeding concentration exceeding 0.25 weight%, and cause a decrease in ferroelectric performance. So in this figure, we can see that 0.15 weight% sample has the greatest average length of elongated rod-like structure, which probably contribute to the highest pyroelectric and ferroelectric properties. The dielectric properties of this polymer nanocomposite studies is shown in these two figures here. So these two figures indicate that the real permittivity increases as the composition of zinc oxide increases up to 0.25 weight percentage, and the dielectric loss shifted to a lower frequency as the fillers of zinc oxide quantum dot increases. And in this figure, we see that the Curie temperature increases about 10 degrees Celsius when the zinc oxide quantum dot is introduced into the polymer nanocomposite. So the increase in real and imaginary part of the permittivities of this composite at low frequency range is due to the effect of conductivity of zinc oxide quantum dots. And we can also see in this figure that the Maxwell-Wagner relaxations is observed at low frequency due to the interactions at the interface between zinc oxide quantum dots and the polymer host. We have also compared our experimental work with several theoretical models of effective dielectric permittivity, as shown in this figure here. So the nanocomposite films is modeled by two-phase dispersion system consisting of the polymer metric of VDF-TrFE and the inclusion of zinc oxide quantum dots. So from this figure, we can see that Cauchy and effective medium theory fits well up with the experimental result up to 0.25%. And EMT indicate that the fitting parameter obtained from the model is 0.9, which indicates that the quantum dot that we synthesize is not actually spherical, which is contradicting to what we have seen from TEM. So larger inclusion of zinc oxide quantum dot, which is with more than 0.25 weight percent, shows that none of the models that we use in this work fits well with the experimental work. So from this result, it seems that higher doping of zinc oxide quantum dots deteriorate the dielectric permittivity, probably to the high leakage current density. So as a conclusion from this work, that we can confirm that the quantum dot size is 2 to 3.5 nanometer, and when 0.5 weight percentage of zinc oxide quantum dots incorporated in the polymer host of VDF-TrFE, it has produced enhancement in dielectric constant, random polarization, pyrotectic coefficient compared to the pure PVDF-TrFE. This is probably due to the greater distribution of meso-like crystallite and also the optimized growth of elongated rock-like crystallite. The maximum energy storage density recorded is 1.18 joule per centimeter cube. The figure of merit calculated at 1 kHz is 19.5 joule per meter cube Kelvin square. Both are exhibited from the nanocomposite with 0.15 weight percentage of zinc oxide quantum dots. And we see as the nanofillers weight percentage increase exceeding 0.25, then the performance of pyroelectric deteriorate. This is due to the formation of meso-like hole structure with depth reaches to the surface of silicon substrate, which has caused the high leakage of current density. So the distribution of this whole look-like structure deteriorate the net polarization of the films and affect the performance and pyroelectric of the polynanocomposite films and their potential in energy storage and energy harvesting performance. I would like to acknowledge the financial support from the Ministry of Higher Education Malaysia under FRGS grant, University Malaya under IRRG scheme, and also University Pertahanan Nasional Malaysia for funding the postgraduate student. So for that, I thank you very much.